We now have an image of that invisible space anomaly, a black hole.
When the first data packets arrived from Webb's Deep Field Survey, no one expected trouble. These were routine observations, follow-ups on a faint, early galaxy cataloged months earlier. But when astronomers ran the spectral analysis, the reaction inside the room changed instantly. Conversation stopped. People leaned toward their screens. There, in the data, was the signature of a cosmic engine far too powerful for its time. A supermassive black hole, weighing roughly 400 million times the mass of our Sun, already fully formed when the universe was just a toddler. This discovery isn't just another entry in the catalog. It puts our entire story of cosmic evolution under pressure. For years, our models were built on a simple premise. Things in the universe start small and grow slowly over billions of years. But this object is like finding a fully grown redwood that sprouted only a week ago. The established timeline for how these cosmic titans are born is being seriously questioned, and scientists are now scrambling to understand what it means. This isn't just a discovery, it's a deep challenge to our most fundamental models, and for some of our most cherished theories, this is going to hurt. To understand just how jarring this is, you need to know what we thought we knew. For decades, the story of how supermassive black holes form was methodical and elegant. It was a story of patient growth over cosmic eons. The process was thought to begin with a massive star, maybe 20 or 30 times bigger than our Sun, at the end of its life. It collapses under its own gravity, creating a stellar mass black hole. This is the seed. It's a respectable starting point, but it's a far cry from the behemoths we see at the centers of galaxies today, which can be millions or even billions of times our Sun's mass. So how does a seed grow into a monster? The answer was always time and food. Over billions of years, these black holes feed on surrounding gas and dust. But this process has a natural speed limit known as the Eddington limit. As the black hole feeds, the intense energy from its accretion disk pushes back on incoming material, throttling its own growth. It's like trying to drink from a fire hose. You can only take in so much at once. The other path to growth is through galactic mergers, where the central black holes of two colliding galaxies eventually combine. This two-pronged approach, steady feeding and occasional mergers, was the cornerstone of our understanding. It works perfectly to explain the supermassive black hole in our own Milky Way and others in the local, modern universe. The timeline adds up. There has been plenty of time, nearly 13.8 billion years, for these slow processes to play out. But the James Webb Telescope is a time machine. It's not looking at the modern universe, it's peering back into the cosmic dawn, to an era just 800 million years after the Big Bang. And in that infant universe, it found this thing, a black hole already 400 million times the mass of the Sun. Therein lies the problem. According to the standard rulebook, there simply hasn't been enough time. For a black hole to grow this big, this fast, through the slow and steady methods of accretion and mergers would be like a human baby growing to the size of a blue whale in its first year. The timeline doesn't just fail to add up, it presents a severe tension with our models. This object challenges our assumptions, and that forces us to ask a difficult question. If our standard theory is incomplete, what is the right answer? Finding a black hole is inherently difficult. They are by their nature black. They don't emit light, they consume it. So astronomers have traditionally hunted for them by looking for the chaos they create. When a black hole is actively feeding, the gas and dust swirling into it is heated to millions of degrees, shining more brightly than entire galaxies. This is an active galactic nucleus, or AGN, a giant neon sign screaming, "Black hole here." But the monster Webb found wasn't screaming, it was sleeping. This 400 million solar mass black hole has a very low accretion rate. It isn't voraciously consuming matter. It's taking him just a trickle compared to the feast required to power a bright AGN. There's no blindingly bright accretion disk, no powerful jets. This black hole is effectively a ghost, hiding in the shadows of the early cosmos. So how did Webb find it? The answer lies in the telescope's unprecedented power. JWST is designed to see the universe in infrared light, which is crucial for peering into the distant past. As light travels across billions of years, the expansion of the universe stretches it into the infrared spectrum, allowing Webb to see things previously invisible. Even though this black hole is quiet, its immense mass gives it away. An international team of astronomers, led by researchers at the University of Cambridge, wasn't looking for a bright light, but for the subtle influence of a colossal gravity well. By analyzing the motion of stars in its host galaxy, they could infer the mass of the central object pulling all the strings. Its dormant state was actually an advantage, letting scientists study the host galaxy without the blinding glare of an active quasar. This discovery is a testament to Webb's revolutionary capabilities. It's not just finding the bright, obvious objects we expected. It's finding the quiet, hidden ones that lurk in the dark. It's like being able to find a whale not by the splash it makes, but by the subtle currents it creates as it glides silently beneath the surface. Finding a dormant black hole of this magnitude demonstrates a level of precision that is rewriting what's possible in astronomy. And in this case, that shadow is casting a long doubt over some of our long-held assumptions. The existence of this giant doesn't just bend the rules, it forces scientists to give serious weight to theories that were once on the periphery. The challenge is explaining how such a monster could be born so quickly. One of the leading ideas is the theory of direct collapse black holes. Remember, the standard model starts with a single star dying, leaving a light-seed black hole. The direct collapse model proposes that, under the unique conditions of the early universe, you could skip the star phase entirely. A colossal primordial cloud of gas, hundreds of thousands of times the mass of our sun, could have collapsed in on itself, imploding directly into a heavy seed black hole of 10,000 to 100,000 solar masses. This gives you a massive head start. For years, this was a compelling but unproven theory. Now Webb is providing the first real evidence that this pathway might be viable. But even a heavy seed needs to grow, and fast. This leads to a complementary idea, a new model of black hole growth. The Eddington limit was thought to be a firm physical barrier, but what if early black holes were more reckless feeders? Some theorists propose that these objects might go through violent, short-lived growth spurts, binging eating gas at rates far exceeding the Eddington limit, in a process called super-Eddington accretion. Simulations exploring these ideas suggest a feast and famine cycle. A black hole might feed voraciously for a few million years, growing at an astonishing rate, before falling dormant for 100 million years after consuming all the nearby gas. The object Webb found could be one of these cosmic giants caught napping after a massive meal. This would explain both its immense size and its current quiet state. It didn't grow slowly, it may have grown in explosive bursts. Perhaps the most profound implication, however, comes from the black hole's relationship with its home. In the modern universe, supermassive black holes are typically a tiny fraction of their host galaxy's mass, about 0.1%. But this new black hole is different. It's estimated to account for up to 40% of its host galaxy's total stellar mass. Let that sink in. It's not a black hole in a galaxy. The black hole is the galaxy, or at least a huge portion of it. This flips the traditional formation sequence on its head. The long-held theory of coevolution stated that galaxies and their black holes grow up together in lockstep. This discovery suggests something far more radical. In the early universe, the black hole might have come first. It may have acted as the gravitational seed around which the first stars and galaxies later formed. We've been thinking of the galaxy as the parent and the black hole as the child, but what if it was the other way around? A discovery of this magnitude doesn't exist in a vacuum. It sets off a chain reaction that ripples through cosmology. If our ideas about the birth of the biggest black holes need revision, so does our understanding of everything they influence. First, there's the mystery of galaxy evolution. For years, astronomers assumed it took billions of years of mergers and settling for the chaotic, irregular galaxies of the early universe to become the grand, structured galaxies we see today. But JWST is consistently finding galaxies that are far more mature and structured than they have any right to be, including surprisingly well-organized disk galaxies. These discoveries, alongside monster black holes, suggest the cosmic timeline is drastically accelerated. The early universe wasn't just a chaotic nursery, it was capable of building massive, complex structures much faster than we imagined. Could these oversized black holes be the missing ingredient, their immense gravity acting as a cosmic scaffold?
Then there's the impact on star formation. Active black holes are known to shut down star formation through feedback, blasting away the cold gas needed to form new stars. But a dormant giant presents a different puzzle. Its immense gravity would still stir the pot, perhaps triggering bursts of star formation in some areas while stabilizing the galaxy in others. Understanding this dynamic, the influence of a quiet giant, is critical to building a complete picture of how the first stars came to be. Finally, when our best models are stretched this thin, it forces us to confront new possibilities. Some researchers are exploring how the behavior of dark matter might have accelerated the collapse of matter in the early universe. Others are revisiting more exotic ideas, like primordial black holes formed in the first seconds after the Big Bang from pure density fluctuations. These ideas were once mostly mathematical exercises, but Webb's detections are breathing new life into them. As one astrophysicist noted, we're not looking at an error, we're looking at a formation pathway that should not exist under the standard assumptions. Every impossible discovery from JWST pushes us closer to a paradigm shift. We are being forced to think outside the box because the universe we are now seeing is proving to be far stranger and more magnificent than we dared to believe. The James Webb Space Telescope is not just answering old questions, it's giving us a whole new set of mysteries to solve. We are living through a revolution in our understanding of the cosmos. If you want to stay on the front lines of this incredible journey, make sure you subscribe and hit the notification bell. Every new image from Webb brings us one step closer to understanding our universe's origin story. So, we stand at a precipice. Behind us lie decades of established theories about how the universe grew up. Before us lies the data from Webb and a single dormant giant that challenges it all. A 400 million solar mass black hole found sleeping at the dawn of time has become one of the most significant cosmological puzzles of the decade. It challenges the very timeline of the universe, suggesting the cosmos built its most massive objects with terrifying speed. It forces us to reconsider the birth of galaxies, hinting that black holes might be their architects, not just their residents. And it shines a light on our own understanding, pushing us toward theories of direct collapse and super Eddington feasts that are now moving to the center of the debate. This isn't a failure of science. This is how science works. Theories are models, meant to be tested, stretched, and refined. And JWST is the instrument that is pushing them to their limits. This is not an ending. It is a profound and thrilling new beginning. It tells us that the early universe was more dynamic, more aggressive, and more efficient than our models predicted. The story of the cosmos is being rewritten right now, before our very eyes. And as Webb continues to stare into the darkness, one thing is certain: there are more surprises out there waiting to be found.